All right, let's see here. Where's the rest of the class? All right, well, I got 11 people in the class right now. I got 7 people in the Desmos activity. 4 of you have not joined yet. Please join the activity. It gives you the opportunity to practice, which is better than not practicing. Either way, we're going to get started here. You can follow along on your own screen. I also do have everything on the shared screen in Teams, so it's entirely up to you how you want to follow along with this. All right, our first screen here, inference for two-way tables. All right, we can use a two-way table to summarize data involving 2 categorical variables. To analyze the data, we compare the conditional distributions of one variable for each value of the other variable. Then we turn to formal inference. 2 different ways of producing data for two-way tables lead to 2 different types of chi-square tests. We have our chi-square test for homogeneity. This is when a study aims to compare the distribution of a single categorical variable for each of several populations or treatments. In such cases, the researchers should take independent random samples from the population of interest or use the groups in a randomized experiment. The null hypothesis is that there is no difference in the distribution of the categorical variable for each of the populations or treatments. The alternative is that there is a difference. For a chi-square test of independence, this is when we have a study that is designed to investigate the relationship between 2 categorical variables. In such cases, researchers take a random sample from the population of interest and classify each individual based on the 2 categorical variables. The null hypothesis is that there is no association between the 2 categorical variables. The alternative is that there is an association. Another way to state the null hypothesis is that the 2 categorical variables are independent in the population of interest. So that's section 11.2 in a nutshell. All right, we have our conditions for performing inference on a two-way table. We have conditions for chi-square test for homogeneity and conditions for chi-square test for independence. They are almost identical except for the randomness condition. For the test of homogeneity, the random condition is that the data come from independent random samples or from the groups in a randomized experiment. Independent random samples basically implies that we're sampling from 2 separate groups or 2 separate populations. All right. With our test for independence, the random condition is that the data come from a well-designed random sample. We're only sampling from a single population for this test, so we're not doing multiple samples or anything like that. Right, or a randomized experiment. 10% and large counts are the same for both. We need to make sure that when sampling without replacement, that our sample size is less than 10% of the population we're sampling from. And our large counts, all expected counts are at least 5. The way that we find our expected counts is the same for either test. When we're doing inference on a two-way table, this is how we find the expected counts, whether it's a test of homogeneity or a test of independence. When the null hypothesis is true, the expected count in any cell of a two-way table is the row total times the column total divided by the table total. And you use that method to find each expected count for each cell in the two-way table. We've got our quick rundown here for the chi-square test for homogeneity. These are the things that you will be doing once you've checked conditions. Right? You can use the chi-square test for homogeneity to test the null hypothesis that there is no difference in the distribution of a categorical variable for several populations or treatments versus the alternative that there is a difference in the distribution category. We're going to start by finding the expected counts, then calculate the chi-square statistic the same way that we have for all chi-square tests. We have the sum of all the observed minus expected squared divided by expected, where the sum is over all cells, not including totals in the two-way table. If the null hypothesis is true, the chi-square statistic has approximately a chi-square distribution with degrees of freedom equaling the number of rows minus 1 times the number of columns minus 1. Again, our degrees of freedom for a chi-square test are based on the number of categories, not the sample size. The p-value is the area to the right of chi-squared under the corresponding chi-square density curve. And then we have our quick rundown for the chi-square test for independence. It is essentially the same as what we just saw, except now our null and alternative hypothesis have to do with association or independence. Right, we can write our null hypothesis as there is no association between two categorical variables in the population of interest, versus the alternative that there is an association between two categorical variables in the population of interest. Or we can state this in terms of independence when we say the null is that two categorical variables are independent in the population of interest, versus the alternative that two categorical variables are not independent in the population of interest. After that point, the process is exactly the same as the chi-square test for homogeneity. So next here, we're gonna look at a short video. Hopefully this cooperates with me today, showing how to do chi-square tests for two-way tables on your calculator. This can be incredibly helpful. This uses matrices on your calculator to input the data from a two-way table, and then your calculator finds your chi-square statistic, your p-value, right? All that fun stuff that you'll want. It can do that for you, which saves a ton of time. Right? Doing these things by hand can be very time consuming. All right, so let's see if I can make this work. Please let me know if you can hear it.
Hello, this is Lee Natero. In this video, I'll be showing you how to do a chi-square test for a two-way table using the TI 8384 calculator. We'll be using an example that's found in Chapter 11, Section 2 of the Practice of Statistics. In this example, we're interested in seeing
Thank you for letting me know you can hear it, Devin. That's helpful.
if there's no difference in the true distribution of entrees ordered when no music, French accordion music, or Italian string music is being played. To begin, we'll enter our data in matrix A. Hit second, X to the -1, go over to edit, and choose edit matrix A. We don't want matrix A to be a 1x1 matrix, we want it to be a 3x3 matrix. So hit 3, enter, 3, enter.
Real quick, when you're entering the size of a matrix, the first number is the number of rows. The second number is the number of columns. Right, so the first value, if matrix A is a 3x3, it's saying it has 3 rows and 3 columns. If it was a 4x3, we would have 4 rows and 3 columns. So that first number you enter is the number of rows. Second number for the dimensions of the matrix is the number of columns.
And now we can fill in our matrix. Now that our data is entered, we're ready to run the test. Hit second mode to get back to the home screen. Then hit stat, go over to tests, and scroll to find chi-squared test. I'm going to hit the up arrow since I know chi-squared test is near the bottom. This is a little quicker way to get there. Chi-squared test. And we need to tell the calculator where our observed matrix is stored. It's stored in A, not E. So I need to change this. To change this, hit second, X to the -1, and then hit enter on matrix A. The expected counts are going to be stored in matrix B. We'll leave the...
Obviously, the part that's not being shown here is that the person who made this video has input the values for both the observed and expected counts in 2 separate matrices. On your graphing calculator, if you have not used matrices before and you have not used the chi-square test before, it will default to have matrix A as observed and matrix B as expected. You will not have to change them unless you've changed them previously. Okay.
Color is blue, and we'll come down here to calculate. Our chi-square test statistic is about 18.3, and our p-value is 0.001. This means we have a statistically significant result. So we would conclude that there is a difference in the true distributions of entrees ordered when the different types of music are being played. We also have the option of drawing the chi-square distribution. So let's go back to chi-square test again. And instead of choosing calculate, let's choose draw. We can see the chi-square distribution being drawn, and at the bottom of the screen we see the chi-square test statistic and the p-value. Because this p-value is so small, we don't really even see the shading in the end of the distribution here.
All right, so that is a quick look at how to use your calculator to do a chi-square test for two-way tables. This is definitely something I suggest that you practice. You'll have an opportunity to do that today, because being able to do that will save you a bunch of time. So that brings us to the first question. All right, we're going to be filling in expected counts. All right, so we have this big old context here. Has modern technology changed the distribution of birthdays? With more babies being delivered by planned C-section, Miss McDonald's statistics class hypothesized that the day of the week distribution of births would be different for people born after 1993 compared to people born before 1980. After all, why would a doctor plan a C-section for the weekend? To investigate, they selected a random sample of people from each of the two age categories and recorded the day of the week on which they were born. The results are shown in the table to the right. Is there convincing evidence that the distribution of birthdays has changed? We're going to calculate the expected counts for the two age groups, assuming that there is no difference in the distribution of birthdays. Please round to 2 decimal places. All right. Also, if you look at the top of your screen, you do have a calculator. Right? That might be useful if you don't have your graphing calculator available. I do suggest if you do have your graphing calculator that you use that and not the built-in calculator here. However, just to show you how to find the first entry for the table. All right, remember, each cell, we can find its expected count by taking the row total of that cell times the column total that that cell is in, divided by the table total. All right, so for the first entry here, for Sunday before 1980, we will have 21 times 77 divided by 150. That gives us 10.78. 10.78 is what will go in the table right there. Right, for the second row, or I'm sorry, the second entry here, Sunday after 1993, second column for row 1. It's still 21s, but now it'll be times 73 divided by 150, and we get 10.22. Right, notice the table will tell you that the answer is correct. Set up so that you get immediate feedback there. All right, so we'll follow the same strategy to fill out all the entries in this table. We're going to give y'all a few minutes to work on this, and then we will discuss. All right, that may or may not have been enough time for you to get most of that table done. Whether it was or wasn't, that's fine. The bigger idea is that you got an opportunity to practice getting these values, and that of the ones that you did do, hopefully you got them correct. Yeah. Are there any questions about finding our expected values on a two-way table?
Do we have to round them?
In this case, I asked you to round to 2 decimal places. So yes, most of the time you'll get, or it's likely that you will get a decimal that's rather large on some of these. So I would recommend rounding. If it's not specified how much to round, I would probably recommend keeping like 3 decimal places. I suggested 2 here because it makes it fit in the viewing window of the table better. So yeah, that's kind of the idea. But technically, the more decimal places you keep, the more accurate your results will be. But at a certain point, there's like diminished return, so to say, on keeping decimal places. It's not going to have enough of an effect on the overall answer to keep them all. Does that answer your question?
Yes.
Awesome. All right. Next. All right, so we have tables pictured below, or pictured to the right here. We have observed at the top there and expected for the bottom. Please note that the expected counts provided here are from the textbook, as this is an example from the textbook. And somehow their expected counts are not what they should have been calculated to be in some of the rows. I'm not sure how they messed them up, but some of their decimals are about 0.02, 0.03 more or less than they should be in some of the rows, compared to what we calculated on the previous screen. It's just an error in the textbook, and however, this next part is based on these 2 tables, so please use the values in these 2 tables. All right, we're going to use these 2 tables to calculate the chi-square statistic. All right, in the entry window here, please just type in the value and round to 2 decimal places. I do not need you to type in chi-squared equals. I don't need you to show the addition of all the different fractions with observed minus expected squared divided by expected. I just ultimately want you to type in what you believe the chi-square statistic is numerically. Right. Again, I suggest using your graphing calculator if you have that to practice using the matrices and finding the chi-square statistic that way. All right, let's look at how we can do this one. All right, so if you're trying to do this by hand and calculate all 14 components to this chi-square statistic, you did not have enough time to do that. That's going to take a while. The best strategy here is to be able to use your graphing calculator. Hopefully all of you have a graphing calculator. If you don't, you really should get one. Go check one out from your school. I believe most schools have enough to check out to people, at least schools in our district. So please make sure you have one. That's going to be really, really, really helpful. All right, so let's do this. Here is our calculator. We're going to use our matrices to do our chi-square statistics. So we're going to go to second, x minus 1. Above that it says matrix. That's where we're going to edit our matrices. We're going to go over to edit, enter. On that first matrix A, we're going to change this to a 7x2 matrix. Right, as we have 7 rows and 2 columns in our data. We're then going to go through and just type in all the values in the same way they show up on this table. All right, we're going to have 12, 9, 12, 11, 14, 11, 12, 10, 7, 17, 9, 9, 11, and 6. All right, so we've put in our values for our observed counts. Next, my mouse will go to second matrix again, go over to edit, and go to matrix B. And we'll set this one up again as a 7 by 2 matrix, 7 rows by 2 columns. And now we'll put in all the other values here. We've got, make sure this works, 10.78. All right, 10.22, 11.78, 11.17, 12.86, 12.19, 11.32, 10.73, 12.32, 11.68, 9.24, 8.76, 8.7, and 8.25. And we have all of our observed counts based on these two tables of information we've been provided. Next, we'll go to stat. Click over to tests. We'll go to chi-square test, which is option C. Hit enter. All right, calculator has defaulted to have observed for matrix A, expected for matrix B. And we will calculate. And there we go. We have our chi-squared statistic at 6.5491199. All right, we will round that as requested at 2 decimal places here, 6.55. We have a p-value that's also been found. It's 0.36456, on and on. And we have degrees of freedom equaling 6. Okay. And again, the degrees of freedom are 6 because we have 7 rows and 2 columns. 7 minus 1 is 6. 2 minus 1 is 1. 6 times 1 is 6. There's our degrees of freedom. All right. So if we can get our data put into our matrices here, it allows us to find the chi-square statistic and a p-value, which can move things along in doing our significance test very nicely. All right. So there's that. I also want to show you that the calculator actually fixed the expected counts matrix based on the observed counts that we put in. So again, this illustrates that there was an error in what the textbook did. But the calculator went ahead and adjusted that, fixed the error essentially, so that we got the accurate solution. So that's kind of nice. All right. And that's good for that. So now we have our chi-squared statistic is 6.55. Right. The hypotheses for the birthday study are the null hypothesis that there is no difference in the distributions of birthdays for people born before 1980 and people born after 1993. The alternative is that there is a difference in the distributions of birthdays for people born before 1980 and people born after 1993. The value of chi-squared equals 6.55. We're going to assume that all conditions have been satisfied. We're going to use table C to find the p-value, then use a chi-squared CDF command in your calculator to also find the p-value. We have a small excerpt of table C, which contains the part that you will need. I do not know how small that shows up on your screen. I'm going to put a link to the formulas and tables in the chat here in case you would prefer to use that. That's going to be right there. It links back into Canvas with that document. So find the chi-squared statistic on table C, or I'm not, sorry, p-value. All right. If you notice the way that we have this set up here, we have my p-value set up to just be greater than a certain proportion. That's not a mistake. It is only going to be a one-sided inequality here. And then you'll get an exact value for the p-value using the chi-squared CDF command, or you can use the result that we just saw if you have the matrices in your calculator for the p-value that was found there. They'll get almost the same value. They're slightly different. We'll give you all a couple minutes here to do this, and then we will discuss. Alrighty, so here we go. Let's talk about this. It seems that some of you got the exact p-value. That's great. And the p-value from table C is probably a little bit confusing, so we're going to talk about that. Let me pull up a copy of table C. Get my stuff to do what I want it to do. Let's get to table C. All right. So hopefully you can see on the shared screen here, we have table C, which are our chi-square critical values. When we go to 6 degrees of freedom, which is our degrees of freedom for this particular test, notice that every value to the right, every value in this row is greater than 6.55, which is our chi-square statistic value. All right, that means the chi-square statistic for this test, the 6.55, is somewhere over to the left of 7.84, which means the tail probability, the p-value that we're going to use, is greater than 0.25. In this particular case, because our chi-square statistic, our test statistic, does not fall between two values in our table, it's only less than a certain value, that means we're just greater than a certain tail percentage, which in this case is 0.25. We could have the same thing happen on the other side of the table. Right? If I have a value that is only greater than 24.1, like I get a chi-square statistic of 27, then it would result in a p-value being less than 0.0005. Right, so there are cases in table C where we don't end up with a range necessarily, an upper and a lower bound for the p-value. We can just say that it is greater than something or less than something. Okay, is there anything to clarify with that? And does that make sense? All right, so we have 0.25 here. And then again, if we go into the calculator, right, we have a couple options in calculating our chi-square statistic. We could do what we did with our matrices previously to find the chi-square statistic that automatically delivered us a p-value. Or we can go to distributions. Oops, I did not hit second first. Distributions, right? And we can use the chi-squared CDF distribution. Right, option 8 here. Use 6.55 as the lower bound. Have an upper bound of just some large number, right? Because there is no endpoint. We're just looking for what proportion under the curve is greater than 6.55. Degrees of freedom of 6. I didn't do what I wanted. Where'd it go? Oi. Why is my calculator not cooperating with me? Try this again. There we go. And we get 3.6447, blah, 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 right? We can round this 3.645. Right. If you use the p-value from the other result, I believe it's a slightly, I don't remember if it's bigger or larger, I'd have to look again. However, they're not different enough to throw off our results. So whether or not, with whichever method you used, the important thing is that they'll both be okay. And also, on the AP exam, you need to say which method you used. Don't just miraculously have a p-value that you're not telling anyone how you got it. Tell them what functionality in the calculator you used. All right. Is there any questions on this one here? All right. Let's get on to the next one. All right, so this one has 2 questions to answer, 2 things to do. So we have our p-value from the birthday study is 0.3645. We want you to first interpret the p-value in context, and then write the conclusion based on that p-value. So remember, when we're interpreting in context, that means saying, what does this proportion represent? The conclusion is then saying, how does this proportion compare to our significance level, the alpha? And what does that mean we get to do about our null hypothesis? Do we reject or fail to reject? So we'll give you all a few minutes here to type in some responses, and then we shall discuss. Okay, so some of you are able to get both of these parts done. Some of you are still working on both of these parts. That's totally okay. The key thing is to understand that there is a difference between these 2 prompts. Interpreting a p-value is saying, what does this proportion represent? What is it a probability of? The conclusion is comparing that p-value to the significance level and stating whether or not we reject or fail to reject the null hypothesis, which many of you are doing very, very good at. But the interpretation is the other part of this that you might be asked to do. All right, so here's one possible way to interpret the p-value from the calculator in context, assuming that the distribution of birthdays is the same, which is another way of saying that there is no difference in the distribution of birthdays. All right. There is about a 0.3645 probability of observing a difference in the 2 distributions of birthdays among the 2 age groups as large or larger than the one in this study. That is what this proportion represents, the chances of seeing the results that we saw if the null hypothesis were true. For the conclusion, which many of you have done very good with, we have, because the p-value of 0.3645 is greater than alpha equaling 0.05, which again, we were not provided a significance level, so we use the default of 0.05. We fail to reject the null hypothesis. Right, we do not have convincing evidence that there is a difference in the distributions of birthdays for the people born before 1980 and the people born after 1993. Right. Is there any questions? Why is this over here? Oops. Right. All right, this next page is just an information page here. Which chi-square test to use? To help recognize which test to use for a given context, you should think about the date, how the data were collected. All right, take note of the number of populations or groups and the number of variables. Here's a summary. For the goodness of fit test, which we saw in 11.1, there should be 1 variable and 1 population. Right, we get a one-way table. For homogeneity, we have 1 variable in 2 or more populations or groups. So we have 1 response variable we're collecting data about, but we're asking 2 separate independent groups or populations about it. Or we're tracking that variable between different treatments in an experiment. Right? And then we have the test for independence, and this is when we have 2 variables in 1 population. So we sample randomly from a single population of interest and then categorize these people or things based on 2 variables. So that's the basic idea. We want to check how the data was collected, and that tells us which test to use. And so the last slide here is some multiple choice questions about which chi-squares test should you use. Carefully read the 3 given contexts below and select the appropriate chi-square test that should be used. You do not need to perform any calculations or actually perform the significance test. Just select the proper test. So I'm going to give you all a few minutes here, and then we will review it, and then we will be done. Alrighty, so let's go through these real quick. For the first situation here, this ends up being a test for independence. If we look at the last statement within that context, we have a random sample, a single random sample of 1,000 adults, and they're asked whether they regularly attend religious services, one variable, and whether they drink alcohol daily, a second variable. So we're going to collect all our data and then categorize the adults in our sample using the 2 variables. All right, the next scenario here, this is a test for homogeneity. And this is because we have 2 separate populations, Canada and US, and we're collecting data about a single variable, right? The patient's own assessment of their quality of life relative to what they had before their heart attack. Right, so 2 separate populations that we're separately sampling from and then collecting data about a single variable. Lastly, this one is a test for goodness of fit. In this scenario, we have a single population and a single variable that we're collecting data on. The single variable is the combination of wing shape, I believe, and eye color. Right, and there's only a certain number of different combinations of that, and so we're collecting data on which combination of those 2 things the offspring of our fruit flies have. But there's a single population that's being sampled from and a single variable that is being tracked. So that's a goodness of fit test. All right. Are there any questions? Anything I can clarify? Alrighty. Then that brings us to the end of the activity and the end of the lesson. If you do have any other questions, comments, or concerns, please be sure to let me know. Other than that, I hope you all have a great rest of your day. Have a great weekend, and I will be seeing you next week.